School of Electrical and Electronics Engineering, REVA University, Bangalore. It's my pleasure to welcome resource person of the day, Dr. Rajashekar P. Mandi sir. Dr. Rajashekar P. Mandi sir obtained his MTech degree from VTU Belgavi by securing third rank in Energy System Engineering. He obtained PhD from National Institute of Technology, Surathkal, Karnataka in 2015. He is a certified energy auditor from Bureau of Energy Efficiency, Government of India in first batch, presently serving as professor and director in School of Electrical and Electronics Engineering, REVA University since 2015. Has more than 26 years of experience in Premier Research Institute under the Ministry of Power, Government of India at Central Power Research Institute CPRI in the area of energy auditing of thermal power plants, hydropower plants, process industries, research and academic institutes, and others. He was nominated as Nodal Officer in Elur Circle of Andhra Pradesh under the prestigious project of Accelerated Power Development and Reforms Program APDRP sponsored by Ministry of Power, Government of India for strengthening of electrical distribution system apart from working in other companies. Presently, he is appointed as a Chairman for Expert Appraisal Committee Industry 3.0 by Ministry of Environment, Forest and Climate Changes MOEFFCC, Government of India. He is also chairman and president of several BIS committees. Being an active researcher, he has published more than 150 research papers in reputed journals, conferences, 8 book chapters, and 5 patents. He has delivered more than 180 lectures at reputed institutes, including IIT Bombay, NIT Surathkal, NIT Tiruchirappalli, CPRI, PSTI, and many others. On behalf of everyone, I welcome you to the session, sir. We are waiting for the talk. Over to you, sir.
Thank you, Professor Ankaya. Yeah, thank you for my introduction. Let me start my presentation. Yeah. Good afternoon to all of you. Now myself, Dr. Rajashekar P. Mandi. I will be talking on this environmental impact assessment of thermal power plant. In this, I am going to discuss on the environmental impact of this thermal power generation, how it is causing pollution, environmental pollution, how it is responsible for causing this pollutions. Okay, that I am going to discuss with some case studies and some facts and figures I am going to discuss with you. Okay, if you have any questions or this one, yeah. Mute again. Huh? Huh? I will do. But this is what I did.
Good evening, dear participants. The session will be again continued within 5 minutes. Just I request all the participants to mute yourself. I request Dr. Rajashekar P. Mandi sir to carry on with the session. Over to you, sir.
Yeah. Sorry for the interruption due to some technical issues. I think some problem was there. Anyhow, we will restart. Yeah, let me start this environmental impact assessment of thermal power plants. I am going to share some of the practical aspects of the energy audit, what we have conducted in thermal power plant, how it was relating to the environmental issues. Just I thought I can share my experience with all you people. If you have any questions, you can send it through the chat box or even through the interactive session also you can have it. Okay, with this, let me start. Now, why environmental pollution? Why we have to concern about this environmental pollution? That is mainly because our power generation, now as of now, our installed capacity is around 374 gigawatt. In that, almost around 63% it comes from the thermal route. Okay, that's what that is a major concern about our environmental issues. And presently, major power comes from the fossil fuel. And also, one more major concern is some of the plants, whatever all they have installed during 70s and 80s, their performance is very, very poor. Still, because of the economic considerations, but already a lot of things is done by the government to revamp those power plants. But still, some of the power plants they are operating with a very poor performance. Okay, that is also a major concern about the environmental issues. And hesitation in technology upgradation, that is also a major concern because almost all the older power plants, that is subcritical cycle thermal power plants we were using, now supercritical has come, ultra supercritical have come, and then IGCC technology also has come. But even with all the things, but still we are having that many of the power plants, they work on a subcritical power plants. Okay, that's what, and also technology upgradation like variable frequency drives and so many things. Still many power plants they are not adopted. Okay, that's what this environmental concern. Now, there are two top major problems in the world, that is a climate change and also CO2 emission. CO2 emission is the major concern. You can see the graph is going very, very high steep actually between 2000 to 2010. Now it has slightly steadied, but still it is keep on increasing. Okay, and then effects will be the global warming, and then again this one, sea level rising. Okay, these are the issues with the CO2 emissions, because CO2 emissions, if it increases, it will cause the this one. And one more major concern with the CO2 emission is that is ozone layer depletion. Okay, those are the issues with this CO2 emissions. Okay, any of that we will study in detail. Other is the major energy concern. Majority of the power plants, they work on this coal-based power plants. Okay, these are the, and also one more thing, this coal is a finite source of energy. It is going to be over. Actually, this is the estimate. It was done very, very long back, around 2008 it was done. But now again, these figures have increased. The global, what they have said is 861, but it has crossed almost around 2000. This one in India itself, you see what they have mentioned in this case, it is around 61 billion tons. But recent survey, what they say is around 308 million ton of coal is available in India. Okay. The major concern with that coal, this CO2 emission, because we are converting the carbon into carbon dioxide. That is, world average, it is around 964 tons. That is 0.96 ton per kWh. Okay, that is the MWH. Oil is around 726 and gas is 484. Anyhow, we will see in detail with the Indian. And major concern about this one, by the time around 2035, it will go up to around 28 trillion kWh. That is the estimation of the electricity generation. Again, still in that, you can see the coal play a major role. Okay, coal play a major role. But one more thing is now renewable energy is also taking overtaking because of the government's the present government initiation. Almost any of that we will discuss in the next slides. Okay, this is regarding the carbon emission. You can see here, India, we have the less carbon emission, we can say, compared to the other countries, and also per capita, that is the carbon emission per capita is our India is the lowest, we can say, that is 0.21 compared to other developing countries or developed countries. Okay, but China you can see around 0.58, 0.9, and US you can see that is 5.41. The major this one difference is because their per capita energy consumption is very high. US is almost around 12,000 kWh per person per year, but whereas in India it is hardly 1,020 kWh per person per year. That's what we have carbon emission per capita energy. This one is much lower than the world average. Okay. Yeah, this also you can see the carbon factor, and with respect to the Indian energy economy, you can see that is it has risen from 0.3 to almost around 0.6. Okay, but still our this one is much below than the China and US. Okay. Yeah, this is the energy consumption. This is also around 2010 figure, almost around 21,000 TWh per year. But again, up to this one, almost we have crossed around 30,000 terawatt hour per year is the energy generation, and then CO2 emission accordingly, it is around 28,000 million tons. This is the world average. And also in that you can see that is the major concern of CO2 emission is through the power generation. Okay, emission generation from coal, you can see, which is almost around 12,000 as of 2010. Okay. This is the Indian scenario. Okay, in Indian scenario, that is the CO2 emission is almost around 1,600 million tons as of 2010, as per the IEEE reports. Okay, but again it has increased because after around 95, the increase is steep. Yeah. Now, as per the peak demand and this one, if is concerned, you can see the peak demand is increased. It is increasing. Almost it is around 177 gigawatt is the peak demand, and the deficit between the supply and demand is also coming down because of the government's initiation to set up many of the this one, ultra supercritical this one mega power plants. Almost around 5 mega power projects have come. That is consisting of around 800 megawatts into 5. That is a 4,000 megawatt in a single station. Okay, like that initiation by the government of India, and also a lot of this one, private people, private generating companies, and then again renewable energy systems. Okay, with that our peak demand and supply, the gap has reduced. Almost it is around 0.8. Okay, that is not a major concern.
Anything.
And similarly, regarding the energy supply also, the deficit and the demand is almost, it has come to 0.6. And many of the power plants are forced, this one, they are also being, they are taking outage because of the non-availability of the demand. Okay. Now, this is the scenario okay, the installed capacity in India. This is as per the August 31st, but now as of now, it has increased to around 374 gigawatt. Another 2000 megawatt has been added now for last some 3-4 months. Okay, now in that, why I am showing this is you can see the coal and lignite based power plant is almost around 55.3%. Okay, gas is 6.7. Oil, it has come down because oil based power plants, almost oil based power plants, they have converted into natural gas. That is one of the example is in Tata Power, that is 500 megawatt oil based power plant is fully converted into natural gas. Okay, and then hydro is around 12.3. Nuclear is slow phase. I think it is 1.8%. Renewable is the major, this one, what we can say. Almost around 89 gigawatt power is being generated. That's what our Prime Minister's aim also is by 2022. It will be around 175 gigawatt our plan to set up the renewable energy. After around 35, I think maybe around 2030 or 35, we are going to, our renewable energy is going to cross over the thermal power plants. Anyhow, that planning report is there. Anyhow, that we will discuss. And regarding the generation addition capacity, that's what I was telling. You can see here, still this one, addition, thermal is the major, but after that, you see, after that around 2014 onwards, lot of renewable energy power plants have come. That's what the change in this one, you can see here bottom, the green has increased, okay? That is mainly because of the government's initiation to go for renewable energy, because our Prime Minister, Honorable Prime Minister and the France Prime Minister, they have started this ISA, that is International Solar Alliance. Okay, in that 121 countries have come, that is initiated by our Prime Minister. And these two, countries, they are going to train them and then give the technical support for setting up of the solar PV power plant. Under that, we are going to start some MTech program also in REVA University, okay, to train those engineers from overseas, that is from the 121 countries, okay. Yeah, that's what I was telling. You can see here as of June 19, the coal generation is around 201 gigawatt, renewable is 79, hydro. Okay, now by 21-22, that's what even other day also our Prime Minister, he has mentioned that in one of the conferences, he mentioned that by 2022, we are going, our renewable energy will go up to 175 gigawatt. You can see here by 26-27 itself, you can see our plan is to go for renewable energy more than the coal-based power plant, that is 275 gigawatt. To reduce. This will help in controlling our environmental issues. Okay. Yeah, the major concern of this one, emissions with respect to the India average, this one is 0.955 kg per kWh. Okay, SO2. SO2 is slightly on the higher side in this, but still it is less for the Indian coal. And NO2. Yeah, just let me tell, this is based on the data available from the internet. I have, and with the literature survey, I have just calculated the major concern about the CO2, because you see a person, you see, he will also release the CO2, that is around 42 gram per hour. Okay, that will come to around 1 kg per day. Okay, to compensate that, because the trees, what they do is they absorb the CO2 and then they release the oxygen. To compensate that 42 gram per hour of a person, actually number of trees means by considering around 125 crore population, for that the person, that is 18 trees per person is required to compensate that CO2 emission. Okay, for that to compensate our population, at least 23,400 million trees are required to compensate that. This is for the general ecological balance. Earlier days, what was happening, whatever the human being they used to exhale CO2 is being absorbed by the trees, and they used to give out the oxygen that was taken by the human being. That's what the ecological cycle, it was balanced. Now, because of the industrialization and technology upgradation and the addition of a lot of transportation sectors, electric vehicles, power plants and all, the CO2 emission has increased. That's what I am just comparing with the thermal power plant. You see CO2, the Indian average, considering all the power stations, that's what we have carried out the study also. Compare this one, considering all the even 60 megawatt plant up to 800 megawatt plant. Okay, the average is around 1.05 kg per kWh. Considering around 219 gigawatt of coal power, you see it is almost around 2.3 lakh ton of CO2 is being liberated into the atmosphere. To compensate that, the number of trees required is almost around 100 million trees are required to compensate this. Okay, that's why if sufficient trees are not available to extract that CO2, what will happen? This CO2 will ಇದು ಇದೆಯಾ ಅಲ್ಲ ಇದೆಯಾ ನೋಡಿ ಎಲ್ಲಿ ಇಲ್ಲ ಬತ್ತಾ ಹಾಂ ಇದಾ sorry for the again technical issue. Okay, again the technology upgradation also we can by upgrading technology, that what we can reduce our CO2 emissions. Okay, now the present, that is a subcritical boilers what we are using, that is it is given, it is a world average. Okay, not the Indian this one, just I wanted to show you how it is going to this one. Okay, now this by 2010 it will come down to 743. Then here is the ultra super critical technology up to 20. Then CCS, that is the carbon capture and sequestration. Okay, then if you go for carbon capture method, okay, again there is a cost involvement is huge. Okay, that's what not many people are going for it. Yeah. One more slide, I think it is missing. Anyhow, that as we go up the technologies, even actually if you compare even with the power plant, that is older power plant like 120 megawatt and 140 megawatt, their CO2 specific CO2 generation is around almost 1.4. We have measured 1.4 ton per megawatt like that. Okay. Now this is regarding the power plant. Actually, these are the components in the power plants. Okay, anyhow that we will, you see the major components will be boiler, This is the boiler. In that boiler, we have this water valve will be there, okay, and then economizer will be there, and then superheater will be there, reheater will be there, okay. In this boiler, what happens? The feed water, it comes from the reheater and it goes to the economizer. After economizer, it goes to the boiler drum, and boiler drum, it comes to the water valve. Sometimes we call it as a evaporator also, but in that water valve, what happens? Latent heat of extraction from the combustion chamber, it is extracted, okay. The steam will go up to the saturated level. Then afterwards, it goes to the superheaters, okay. After superheater, it comes to the HPT turbine. Normally, bigger plants, bigger more than 110 megawatt, because less than 60 megawatt and all, they will have only two turbines, that is HPT turbine and LPT turbine. Whereas higher power plants, they will have HPT, IPT and LPT. In some of the places, two IPT will be there, okay. That is what this one. HPT is high pressure turbine and intermittent pressure turbine. Sometimes they will call it as a MPT also, that is medium pressure turbines. And last is the LPT, that is low pressure turbines. After the superheater, it comes to the HPT, then HPT exhaust, because by the time HPT does the work, it will lose the heat in that, the temperature will go down, and then again pressure will go down, pressure will reduce almost to around, it will come to around 30 or 1 kg per pressure, kg per centimeter square. Okay, that reduced steam, after that HPT, again they will pass it into the boiler. Thereby we can increase the temperature of the, that is reheater. Okay, in the reheater, that reheated steam, again it will come to the IPT. Okay, then IPT exhaust will be directly connected to the LPT, and then LPT. After the LPT, it comes to the condenser. Okay. In condenser, almost it will be in a vacuum stage, okay. That vacuum, this one, because here we use the circulating water to convert that vapor into the liquid, because unless you convert into liquid, because your boiler feed pump cannot pump it into a higher pressure. That's what we are using. Almost around 60% of the energy, around 60% of the energy is lost in this condenser to convert vapor into liquid. For that, we are using the cooling circulating water. That circulating water is cooled in the cooling tower and all. From there, it comes to the condensate pump, then comes to the LP heaters, then deaerator, then boiler feed pump. It comes like this. This is regarding the feed water circuit. The other coal and this one, coal comes from the combustion, this one, that is from the crushers and all, okay, and then it will be powdered in the mill. Generally, in our majority of our power generating units, they use a polarized fuel boilers, that is a corner fired, okay, corner fired polarized fuel boilers, okay. That it is polarized in mills, okay, that it comes in the burners here, and it is burnt. That is burnt as it goes up. Actually, it will convert it into flue gas. Then it goes to the different sections, that is air preheaters, goes to the economizer, air preheaters, then ESP, then it goes to the ID fan. Any of that we will see in next this one. Okay, this is regarding the power plant. Now, actually, these are the major equipments in that: boilers, turbines, auxiliary power equipments. In that auxiliary power equipment, ST auxiliaries, that's what I was telling: boiler feed pump, condensate extraction pump, that is a induced draft fan, post draft fans, primary air fans, mills. Okay, and the outlying auxiliaries like CWP, that is circulating water pump, crushers, air compressors. Okay, any of these things we will see it later on. This is the schematic of that. Already I have shown this one. Regarding this one, you can see this is the chamber, that is the furnace. Actually, these are the mill outlet. It comes here, and then coal is burnt here. Okay, and then it comes to the air preheaters. Okay, APH. and then it comes to the ESPs. After that, ID fan it comes, then it goes to the chimney. This is regarding the flue gas circuit. To convert that, this one, air has to be supplied. That is, in air, there are two types of airs. One is primary air and other is secondary air. Both the airs will be heated in the air preheater. That is, secondary air is supplied by the forced draft fans. That will go to the chamber here. That is, a wind box will be there. It will provide the, as you can say, that atomizing air, we can say that. Then one more air, that is a primary air. Primary air is supplied by the PA fans. That will go to the mills. In mills, what happens? That hot air will mix with the coal, and then the main aim of the primary air is to lift the coal from the mill to the burner. Okay, that's what your coal air mixture temperature and the flow is also very, very important in combustion. Okay, then it comes to the air preheater, ESPs, ID fans is the major, this one, we can say it is like a heart of the this one. Okay, if the ID fan trips, whole power plant will trip, because ID fan, it creates the suction, okay, in the furnace. Always it will try to maintain the furnace pressure in negative. You can see here it is minus 5.8. It cannot go to the positive. If it goes to the positive, and there will be a big danger, that is furnace may burst. Okay, that's what the major, this one is the ID fan. This is regarding the condensate and feed water circuit. Already I have discussed. That's what I was telling. You see, drum, it comes to the deaerator, okay, and then after deaerator, okay, it comes to the boiler feed pump. Then it comes to the HP heaters. Okay, this is a reheat cycle. Okay, then it comes to the regenerative feed heating cycle. Okay, then it comes to the economizer and then drum. Okay, then this is the air and flue gas circuit. That's what I was telling. Actually, this is the furnace. That is a corner fire. All these corner, the furnace, furnace burners will be there. They will create a fire here. Okay, then that flue gas comes to the air preheater. Air preheater is a regenerative type of air preheaters. In that, flue gas will be going in one, it will be a trisector. Okay, in that one sector, air will be, this one, flue gas will be going. In other two sectors, one is primary air will be going, and other portion, secondary air will be going. During that time, the heat will be exchanged from flue gas to the primary air and secondary air. Okay, this is what you can see here. We will in here how the flue gas will flow. Actually, this is the furnace. I was telling minus, -6 is there. These are the live figures we have captured. Okay, and then this is the primary superheater, and this is the reheater, and this is the flattened superheaters. This is a final superheater, reheater, and this is a flattened superheaters. Okay, and then convective superheaters, economizer, then comes to the air preheater, goes to the ESP here will be there, and after that it goes to the ID fan. Yeah, these are the regarding any of this also same thing. Okay, just I will skip. Yeah, the major concern of the power plant is heat rate. What we say is a heat rate. Heat rate in the sense how much kilocalorie is used to generate 1 unit of electricity. That's what, even while workout also we say, no, for each food also how much calorie it gives, like that. Similar way, even in thermal power plant also, to produce 1 unit of how much kilocalories of heat is being used. That is the figure you can see here. These are the different plants. Okay, 500, 250, 210, okay, 140. This is 2254 kilocalorie is required to generate 1 unit. But actually what happens, while operating, you can see here in a particular plant, it is 2561, means it is taking more heat because of the losses in the system. That's what you can see here. Deviation, that is 13.6 is the for 500 megawatt, and as the unit size decreases, you can see the operation limit is increasing. Means these are the major concern in environmental issues. Okay, that's what the plant performance, it contributes more in case of the environmental issues. Okay, these are the operating range. This is for the overall gross heat rate, means that is to generate 1 kWh at the turbine from the your coal. Okay, but this turbine heat rate is only it is taking except boiler efficiency. What is the turbine heat rate? That's what we calculate. Even in this case also, you can see here 6.7 to 11% is the deviation. Okay, for the different units. And next is the boiler efficiency. Even in boiler efficiency, that is what the heat input, that is the coal to the steam generated, steam output of the boiler. That efficiency we calculate. Even in this case also, you can see here these are the designed efficiencies, but the operating efficiencies are very less. We will see what are all the reasons for this lower efficiencies. Okay, and also deviations. Why I am showing this? These are the major concern of increasing the environmental pollutions. Okay. Yeah, these are again different. This one again it depends on the aging of the plant also, because as the age increases, your efficiency comes down. That's what they do is generally in thermal power plant, they take two types of overall. That is, one is annual overall, and other one is capital overall. Capital overall they take once in 5 years, but annual overall they take once in a year. Okay, once in a year, what they have to do? They take about 20 to 28 days. Earlier they used to take more than a month, but nowadays they have optimized. Okay, what are all the prone parts? Only they will rectify and then replace. Okay, but because of the non-availability of the schedule, many times what happens, especially these overalls and all, they take during the rainy seasons. Okay, monsoon, because monsoon all the hydropower plants will be in peak. At that time they will take. But many times what happens, even during that time also, if the sufficient power is not available, they were not giving the clearance for doing the overall. That's what they used to do. They were keep on operating extended period. If it operates in extended period, then again the performance is very poor. That caused the poor performance and caused the environmental issues. That's what you can see. As the age also increases, your deviation, that's what you can see here, it is 16 years. The deviations you can see here, they are all higher side. Okay, this is for the 500 megawatt units. Deviation is not that much this one. You can just see this is for the 250 megawatt units. Any of these data are available, only just I wanted. This is, you can see these plants, whatever they have installed in 29 years. Okay, these are the, you can see here gross heat rate designed is 2397, but the operation is 2642, that particular unit. Okay, around 10.3 is the deviation. And similar way, auxiliary power also. Means to produce the electricity in coal-fired power plant, we need auxiliaries like BFP, ID fan, FD fan, all those. That consume almost around, you see, is 11.29. You may be surprising that it was only 1 year, because this data was collected in 2008. Because the auxiliary power is more, because this is a stabilization period, that is the during one. It is like a bathtub curve. Okay, initially 1 year or 2 years, all the parameters will be deviating more. Once it comes to the stabilization, then it will steadily go. Okay. This is for 140 megawatt. You can see here the average deviation rates are very high. This case 18.6, because as the plants are, and many of these power plants, even 100, 110 megawatt plants, there also deviation is more. Many of the older power plants, they were of a refractory type, tube and refractory type. Nowadays, they have gone for membrane type of water valves. Wherever the membrane type of water valves they have used, the performance is better than refractory and tube type of furnace. Yeah, this is just I thought of giving the this one. What are all the reasons for higher heat rate? Okay, that is, first one is the low combustion efficiency lead to high carbon loss. That is the efficiency. That's what we have seen. The boiler efficiency was less. Okay, if it is less, again, what happens to produce the same steam output? You are burning more coal. You are burning more coal means again you are adding the ash. Okay, more ash and more temperature, your flue gas and CO2 emission. Okay, like that, if your combustion efficiency is improved, then automatically you can reduce all these environmental issues. Okay, then higher forced outages. That is especially these older units, because as the life goes, this water wall, what happens because of the ash content, okay, higher ash content, the erosion rate is more in case, especially in boiler tubes, that is in superheaters or economizer zone. Okay, there your ash erosion rate, it is more for the boilers. That's what. And also many times what happens, this is our boilers are corner fired and fireball. Fireball has to be created in the center. Okay, that's what we are firing from all the four corners to make the fireball to center. Many times what happens if it is a mismatch, okay, burner. And burners also, we have that tilting mechanism. That is minus 45 degree to plus 45 or plus 30 degree we tilt, that is, or maybe 15 degree, okay, we tilt, okay, as the operation, initially when we start the boiler, okay, at that time we try to keep it at the down, as because the heat extraction rate comes down, then we slowly start tilting the burner. What happens if automatically we will be operating that? If operation is not synchronized, okay, one burner may be at 45 degree, other burner may be at 30 degree, what happens? There is no fireball formation at the center. That may cause the erosion of the water wall at the opposite side. Okay, that also will cause the tube failures. Okay, these are the boiler tube failures. Because of that, forced outage has to be taken, because if they get some forced outage, at least minimum 6 to 8 hours it will go, because we have to cool down, we have to attend, then again we have to restart. That we call it as a hot restart. Hot restart, sometimes it may take 6 hours or 8 hours, even sometimes 12 hours. Okay, hot restart. Then poor milling system, poor performance of the milling system, that is the mills. Generally we use 3 types of mills. One is bowl mill, okay, where the performance of the mill, that is a pulverized coal, it will be average. And other is E type of ball mill, sorry, E type of ball mill. Their performance is slightly better. And one more is the ball and tube mill, that we call it as a drum mill, but drum type of mill. In that the efficiency is better, the grinding efficiency is better, but whereas your power consumption, auxiliary power consumption is very high, and then maintenance also, high maintenance is required. Again, it depends on the performance of that. Then lack of maintenance, planning and inventory, low turbine efficiency of the turbines, then high dry gas losses. That is again higher exit temperatures and excess air that cause the high dry flue gas losses, that cause the lower boiler efficiency, poor sealing and heat transfer in the air filter leakages and all, they also cause the lower performance, low condenser vacuum, because condenser vacuum, if any leakage or anything is there, because many times what happens, tubes leakages will be there, that also cause an increase in the this one, means poor condenser vacuum. Okay, that also will reduce the capacity of the plant, thereby your efficiency comes down, and then that cause the poor performance. Then high air ingress, this is also a major concern, because the boiler, you see, boiler flue gas circuit always it will be in the negative, okay, because for a safety reason. Once it goes to the positive, then there it may get burst. Okay, that's what always from the combustion, that is the furnace to the till ID fan inlet, the flue gas pressure will be in a negative draft. Okay, only at the ID outlet it will be positive. Okay, all other places it will be negative. That's what always there is a tendency of sucking of the air. Okay, if the air is sucking, that again what will happen, that higher ingress, it will load the ID fans. Then ID fan capacity comes down and your loading of the boiler comes down. Okay, that is high air ingress. Then poor performance of ESPs. Okay, then again ESPs we use, that is electrostatic precipitators, to collect the fly ash in the flue gas. Okay, that also if the efficiency is low, what happens, your erosion rate of ID fan impeller, it increases, and the performance of the ID fan, it comes down, and at the same time your environmental issues, that is the dust particle, that is the particulate matter in the atmosphere, it goes up. Okay, that cause the environmental issues. Okay, then high cooling water inlet temperatures. Okay, then these are the, we will just now discuss the major concern of environmental issues is mainly because of the coal quality. Okay, that is, if the coal quality is better, then your performance will be better and your environmental issues will be less. Because nowadays what happens, our Indian coal, the quality has gone down, because nowadays, because our boilers are designed with a calorific value of around 4,000 kilocalories. But the present available coal quality is around 2,600 to around 3,000, okay, kilocalorie per kg. Because of that, the burden on the power plant, that's what many of the power plant, because we carried out some study in the Raichur thermal power plant during 98 or 2000. Because of the coal, they were unable to load the plant to the 210 megawatt. They were able to operate only up to 180 megawatt. That is because of the high ash content coal, okay, and lower calorific value. That's what they did. They have gone for importing the coal. In other countries, we have the better coal. That is, you can see here, Indonesian coal. These are the different calorific value coals are available, and South Africa. Then this is Australian coal, and then Chinese coal. Chinese coal is also better. And then ash content, you can see, ash content is very less, because whereas our Indian coal, the ash content even we have measured up to 55%, 55 to 60%. Okay, that way, as the ash content increases, your burden on your ESP increases, and your ID fan, burden on the ID fan increases, and automatically your performance goes down, and that will add up your environmental issues. Okay, yeah, this is some comparison done by some study. You can see here different countries. These are the first 5 power plants are the NTPC power plants, and 6th is the US, and then last is the China. Just you can see here ash content. You can see here 46%, 46, 45, 38, and this is a washed coal. Okay, that we will discuss in the washed coal, this one. And you can see the calorific value 2450, 280, 3000, and this is washed coal. You can see here this calorific value has increased, and your ash content has come down. And whereas US coal, you can see here 6378 and 6087. Yeah, these are the generally designed values. And you can see just in one of the power plant, we have carried out some study up to 2008. You can see here over the period of time, your ash content has increased, and then your calorific value, this green line, you can see here it has come down. Okay, and these are the designed values. And this is what I have shown here. Again, heat rate, I was telling as the calorific value of the coal increased, your heat rate comes down, means your performance will be better. Over the period of time, your heat rate has increased and your calorific value has come down. Sorry. And at the same time, if your calorific value of the coal increases, your specific fuel consumption, that is to generate 1 kWh, your fuel requirement will be less. Okay, and at the same time, your auxiliary power also it comes down if your calorific value of the coal is better. Yeah, and if the calorific value is better, you can see the increased power. That is your power consumption of the your major auxiliaries, ID fan and FD fan. You can see here ID fan. You see so much of this one power. It is reduced almost by about 30% power. You can reduce by improving your calorific value from 2,500 to 4,000. Okay, at the same time CO2 emission, you can see here almost around 0.77 ton per hour for ID fan alone. Okay, then mills, FD fan and PAF fan. Okay, this is with respect to the calorific value. And regarding the ash content, it is other way. That is ash content, if it increases your loading on the ID fan, you can see here it will increase. You see, as the ash content increases, you can see here your power consumption is increased almost around 35%. It increases from 20% to 60% ash content. Okay, and similarly FD fan, PA fans and mills. Yeah, you can see these are the figures. These are the burners. These are the burners. You can see here. This is the good one. After the overall, they have replaced. You can see here. This is how it has become. You see, as you go for a prolonged operation, without taking because every overall, what they do is they will change these burners. Okay, and this is a wind box. Actually, in wind box, what happens? This secondary air will be passed in this, and in this part, the coal will be this one pushed in this one. That is a primary air and coal. Okay, you can see here. These are the major, because what happens again? It depends on your ash content. Okay, in the coal, ash content in the sense in the ash again quartz will be there. Okay, even that quartz, the erosion rate for the quartz is more. Okay, that's what it will eat away the metal. Okay. Yeah, and then again moisture content of the coal also it matters. If the moisture content is more, even your furnace size requirement will be high, and your size of the mills is more, and auxiliary power required by the mill also is high. Okay, and then hard grow index. This is also very, very important parameters. Generally, our boilers are designed with 50. Okay, that is 50 to 55. That is what our Indian coal hard grow index is, 50 to 55. But some of the imported coal, the hard grow index is less. Okay, for that, if the hard grow index is less, means your grinding power requirement is high. Okay, that's what you can see here. The mill power requirement will be high as the hard grow index is more less. Okay. Sorry, this is one of the power plant what we have done study in the that is Mundra. This one, that is a power plant, ultra mega power plant. There they were getting Indonesian coal. Okay, in that they were getting two types of coals. One is economic coal and then other one is Melavan coal. You can see here Melavan coal, the HGI is 42, whereas this eco coal, the HGI is 60. That's what you can see here, the specific fuel consumption of this particular mill, that is high, these are more actually. This is since the HGI is high, then your specific fuel consumption, specific energy consumption is less. Okay, that's what hard groove index is also. It matters on the mill performance, and also the fineness also is important. That is the coal fineness. Okay, it should be below 75%, 70% of the coal. It should be less than 75 microns. Okay, but many plants you can see here in this particular mill, you can see here it is only 57, 67, 55. It is on the this one, means this is passing through. It should be more than 75%. Here you can see it is 77. Okay, this particular mill, you see, it seems to be better compared to this mill. But here you can see here again, in this case, it is more than 80%. Okay, again, what happens, this coal fineness also, it matters in the combustion. That is, if the coal particle is more smooth, what happens? It will escape from the combustion zone because that residence time is fixed. Okay, depending on the velocity of your flue gas, the residence time will be more or less, and the finer particle, it will escape from the combustion zone, and then it will land up it into unburnt carbon in the fly ash if the particle size is very, very small. If the particle size is bigger, coarse particle, then what happens in the combustion zone, before burning, because of the weight, it may fall down, and then unburnt carbon in the bottom ash increases. Okay, that is what you have to optimize the fineness also. Yeah, particle size, this one again, particle size, you see, as the number of percentage passing, below 75 microns, it increases, your mill power, it will increase. Okay. Yeah, and another major problem with this mills is the raw coal. Okay, generally what happens, the coal comes from the wagon, then it comes to the coal handling plant, the wagon tippling, it will tipple the coal, and then it goes to the through the conveyor, it goes to the primary crushers. Generally in some of the power plants, they will have two stages of crushing, and but modernized this one, they go for only a single stage crushing. That is, primary crushers will be there and secondary crushers will be there, and after secondary crusher it comes to the mill. But what happens generally, as per the design, the coal size, it should be around 125 mm. Okay, 125 mm, it has to go to the coal inlet, but the coal output, it should be less than 25 mm size. If what happens, because the construction of the crushers also will be different, because primary crusher, generally they go for hammer type of mills. In hammer mills, what happens, it will be hitting the bigger coal and the specific energy consumption will be less, but your performance of the sizing of the coal, it will be less. Okay, that's what in primary crusher, what happens, it will reduce to around 125 to around 50 mm or maybe 75 mm. Then that goes to the secondary crusher. In secondary crusher, what happens, it will reduce the coal size to below 25 mm. Then after crusher 25 mm, you can see here one of the study we have carried out. You can see here coal below, coal above 25 mm sizes in this after crusher is 19.9, means around 20.3. Generally, we say that the coal size, that 20% it should be. Okay, before this one, compared to this, means at least 20% of the coal should be less, means can be above the 25 mm size. But as the raw coal size inlet at the mill inlet, if it increases, from 5, you can see that this is the one specific mill power, okay, up to 25 mm, okay. As the size increases at the mill inlet, your power consumption, it increases. And also what happens in, especially in this bowl mills, coal rejects will be there. If the sizes is big, okay, mill rejects will increase, okay. And then if the mill reject keep on increasing, then again it is a loss, okay. It is a loss, and then again that is one shear pin will be there. Then that shear pin breakage will be happening. If the shear pin breaks, then again you have to take that particular mill into shutdown, okay. That's what you have to maintain the coal size at the mill inlet at below 25 mm, okay. But whereas tube mills, that is drum type of mill, that constraints will not be there. Whatever you put it in that, even the mill, this one, that is the stones. If the stone comes in this bowl mill, sometimes this one mill will get jammed, or even RC feeder, that is a rock hole feeder, may get jammed, and then that shear fin may be frequent failure may be happening. Okay, these are the issues with that. You can just see here how much is the reject. Generally, the mill reject what we expect is 1% or even below that. Okay. Yeah, you can see here, these are these big boulders. You can see a person is lapping on that. You can just see here. So such a big boulders they get, okay. And then these are the stones. Again, stones also will cause major problem in the mills, okay. Then these stone pickers will be there on the conveyors, because what happens, this stone, they cannot allow inside the mills or even in the crushers. Before that itself, stone picking has to be done, and then they will dump it in the coal yard, okay. Yeah. Then again, I was telling that is a washed coal. Washed coal in the sense what they do is washeries they put. In the washed coal, what they do is they, by washing the coal, they can reduce the ash content. This one, you can see here, this is the ash content, this is the raw coal, and this is the washed coal. You can just see the this one, that is the ash content has reduced. Thereby, your performance of the plant increases because your ash it reduces. At the same time, your CV increases. You can see here, this is the range what we have actually got from the field, okay. And this is also washed coal. And also by doing the washing of the coal, you can reduce the you are almost around 20 to 25% of the coal. This one, quantity, you can reduce the transportation cost also. Generally, washeries, what they do is they keep it at the this one. What is that? Coal. This one, from where this one, collieries. Near the collieries only they keep it, because from there, that transportation cost they can reduce this by using that washer. Some of the performances I will this one, that is plant efficiency increases. Anyhow, this we will see here. This is, we have carried out some study here. You see, by using that, this one, washed coal and this one, ash content, you can see here from 52%, it has reduced to 31%. The CV has increased from 3,000 to 3,500. You can see here the auxiliary power of all this one, especially these fans, it has come down, fans and mills. You can see here about 0.43% of the total auxiliary power is reduced, and CO2 emission is reduced by about 0.94 by using the beneficiated coal, means that is the use of washed coal. Yeah, this is another, this one, Satpura Thermal Power Station, that is the NTPC. They have presented this in one of the paper. PLF is increased from 73% to 96% because if the coal quality improves, your plant loading capacity increases. You see, coal consumption reduced because your specific coal consumption comes down because you are removing the ash. Ash you are not unnecessary, without washing, if you burn, unnecessary, you are adding all the ash into the boiler because ash is having a quartz, this one, erosion rate. you can reduce the erosion rate. Okay, that's what your auxiliary power is reduced. Downtime, especially these boiler tube failures and all, will reduce drastically by using the washed coal. And no fuel support, boiler efficiency improvement by about 3%. Then mill power consumption has reduced because they have presented only this. You can see here in this Dadri power plant, again it is a NTPC where they have 4 into 210 megawatt plant. Oh, this is not milliwatt, it is a megawatt power plant. That is saving in damages, even unloading, that is what happens, when the coal rack comes, they will give the some time to unload that. If you don't unload that and if you don't hand over the wagons to the railways, you see within that particular time, they will charge the damage. Because of that, they are able to save that damage charge because the quantity has come down and it is very easy also. Because again, what happens in a washed coal, they will have a crusher also. In that crusher, the size of the coal also has come down drastically at the collieries itself. Instead of getting these boulders and all, if you have boulders and all, clearing that, it takes time. Okay, that time also you can reduce. That way you can reduce the damage charges, increasing operating hours of the plant. Okay, operation of the, because your mill outages comes down and your erosion rate inside the furnace, it comes down. Okay, increase in PLF means your plant can increase. Okay, increase in utilization factor also, reduction in breakdown period 60%, increase in overall efficiency, increase in generation. Okay, reduction in support of fuel oil, specific fuel consumption comes down, increase in total units sent out. Okay, and then reduction in CO2 emission. Okay, and at the same time reduced transportation of this one. That is what he is telling. That is almost around 6 lakh tons per year. He is transportation cost of 6 lakh ton per year. He is reducing that NTPC Dadri by using this washed coal. Okay. Then this is another Dahanu thermal power plant, that is BSCS, that is Reliance. Okay, their ash generation reduced by 8.5%, PLF increased, okay, cost per unit reduced. Okay, these are the auxiliary power, it has come down. Okay, this is regarding the beneficiated coal, that is the washed coal. Now, coal blending, as I was telling, imported coal, the calorific value is almost more than 5,000 or 6,000. Even sometimes earlier initially, we have seen that Australian coal up to even 8,000 kilocalorie per kg. But the problem with this imported coal is because higher calorific value coal, we cannot burn directly in our furnace. Why? Because our boilers are designed at a 4,000 kilocalorie per kg initially, then later on even some of the boilers they have designed with 3,700 kilocalories. For that particular this one, if you burn the coal, only it can perform. If you go for higher calorific value coal, if you burn like 6,000 or 5,500 or maybe 8,000 kilocalorie, what happens? Your burning of that will increase. Your latent heat extraction has to be increased. Okay, in that case, your size of the water wall has to be increased. Okay, because your latent heat extraction comes down and your superheat, that is the convection superheaters. There, the heat extraction has to increase. What happens? Your superheater temperature, it shoots up because the heat content in the furnace, it cannot be taken away by your water wall because of the constraint. If you burn the high calorific value, that's what happens. It goes to the superheater zone or maybe reheater zone. Then you have to reduce that temperature by using a de-superheating. If you use a de-superheating, then again you are reducing your heat. Okay, then it is a loss. Okay, that's what you cannot use. That is what you have to do. And not only that, one more problem with this imported coal is their ash fusion temperatures are very low. Ash fusion in the sense, now in the coal, what happens? when you burn the carbon will convert it into CO2, and then ash will be there as it is. But if the ash fusion temperature of our Indian coal, it will be around 1600 or 1700, because our furnace temperatures will vary between 1400 to 1500 degrees centigrade. That's what ash will be intact. But whereas in imported coal, especially Australian coal or South African coal and Indonesian coal, the ash fusion temperatures are very low. It will be around 1000 or 1200 degree. But what happens if you maintain the furnace temperature around 1400 degree, your ash will get melted, and then clinker formation will happen on the water wall, and then again it will reduce the efficiency. This problem, even in our Neyveli lignite, we have that problem. Okay, that clinker formation. There also lignite, the ash fusion temperature is low. Okay, that's what these clinker formations are there. That's what they use in this lignite boilers. They use a water deslaggers. Water deslaggers they use. Okay, that's what imported coal. What they do is they cannot burn this one. That's what they have to blend with the Indian coal. Okay, that's what CPRI, we have carried out some studies of coal blending different proportion. Even that also, how much proportion we can go for it. That is 20/80 is the optimum value what we have found out. That is 20% imported coal and 80% Indian coal. We can blend that and then burn this one, and your efficiency will increase. That's what we have carried out. You can see here the ash content. By using the blending, you can see the ash content we can reduce. Okay, then your CV also it can increase. Okay, thereby your performance will improve. And again, blending, how we will blend? There are three techniques they have been adopted, and then they have tried. One is this one yard, that is a blending. In yard itself, they mix with the dozer. That it didn't work out, and then they have stopped that. And another one is the belt blending. In belt, what happens in one coal belt will be Indian coal will be going, and parallelly, that is perpendicular to that, another this one conveyor belt they keep, and then they used to add. Okay, that is conveyor belt bending. But what happens, this conveyor belt bending, if you use the coal in all the this one, all the mills, generally in a 210 megawatt, 6 mills will be there, and whereas in 500 megawatt, 8 mills will be there. Okay, in that 8 mills, 6 will be running and 2 will be standby. Whereas in case of 210 megawatt, out of 6 mills, only 4 will be running. 4 have to run, but presently due to the coal quality and all, 5 mills will be running and 1 will be standby. In all the mills, if you keep the blended coal, the again mill reject, mill reject if it is happening, mill rejects generally in a bowl mill, 1% will go. In that case, even imported coal also will go as a reject. That's what they do is, instead of this one, tire blending they do. Tire blending in the sense, there are 6 tires will be there in a corner fired boilers. That is A, B, C, D, E, F. In that, one mill they go for imported coal. Remaining all the 4 mills they go for this one, Indian coal. Thereby they can increase the efficiency. That's what here you can see for a 210 megawatt plant. I have this one. Mill B, generally what they do is they will keep in between mill with the imported coal. All other, that is bottom and top mills, they go for Indian coal. That's what you can see here. The calorific value of that is 6,130. And specific fuel, the specific energy consumption you can see here is 9.54. Okay, thereby you can improve the performance. You can see here the performance also, calorific value. You see raw coal is 3,000. After blending, average if you take it is coming around 3,940. You can see here the auxiliary power is reduced by all the fans. Okay, fans and then mills. And then CO2 emission is reduced by about 0.92 ton per hour. Okay. Yeah. These are the boiler efficiencies. Okay. Again, this also one of the power plant we have carried out. This is also boiler efficiency. You can see in this the major losses will be dry flue gas losses. Dry flue gas losses here you can see here it is around almost around 4.53 is the designed value, but whereas the operating was 5.56, mainly because of the higher exit temperatures and O2 loss in moisture. Okay, again, this will take more time. Just I will compare here the boiler efficiency. 86.15 is the designed value, but whereas the operating is 76.55%. The major concern is wet flue gas, that is the H2O in the coal. Okay. Yeah. Then again, plant load factors are the major concern. Plant load factor, again, your performance depends on the plant load factor. That's what different megawatt plant load factors vary from 93 to even this 120 megawatt and all. Their power plant load factor is low. That caused the poor performance. Again, we have carried out some study in the Hanu power plant, that is a Reliance, that is using a different coal. You can see here poor coal. You see good coal with a CV of 4,600. There they were using a Indonesian coal and the Indian coal also. Good coal. You can see here the ID fans, current is less. But whereas poor coal, if you use, the ID fan current has gone much. And here you can see here the plant capacity also we have seen. You see the margin is very, very less in case of the poor coal. Okay, that's what your efficiency will be less, your auxiliary power consumption will be very high in case of the poor coal. Yeah, here you can see the efficiency of the ESPs also. You can see here, this is the exit, your efficiency, but generally what they say is ESP's efficiency will be 99%. But what happens if your ash content is more, the burden on the ESP also will increase, and then your efficiency comes down. And if your collection efficiency is less, the ash content, it goes, and this one, your ID fan has to handle, okay, that cause the more erosion of ID fans and this one. Yeah, this you can see here, again, you see some of the ID fan impeller erosions, and this is one of the, this one, what is that? Air ingress. Air ingress also causes the loading of the ID fans. You see one of the power plant, you can see this is the ash. It is a puffing. Actually, this furnace is working with the positive pressure. Okay, that's what you can see here. Manholes. These are all causes for the air ingress. You can see here. Just I will skip some of the things. Yeah, here you can see these are the openings here, air leakages in the ducts. If it is air leakages in the duct, what happens? The additional air, because this air will not take any part in the combustion unnecessary, your excess air will increase. If the excess air increases, your dry flue gas losses will increase, and at the same time your exit flue gas temperature increases, and that causes the environmental issues, and your ID fan loading will increase. These are the manholes they have provided, but they have not closed it, but they have kept it open. Yeah, and also insulation on the boiler drum. You see that is not there, and you see these are the leakages. You can see here a lot of ash and ash popping we will call, and this is the blow down. That is a blow down of the this one. Okay, these are, again, you see this is a positive pressure. You see this, it's coming out. The flame is coming out. It is very dangerous to go around this one. That's what the temperature surrounding of the boiler, it will be more because of this popping, and that's what I was telling. You see the furnace pressure at the furnace, it will be negative side. This all will be negative. Only at the ID fan outlet it will be more. Okay, air leakage. And this one, flue gas pressure drop in the APH, that also cause this one, that is the more auxiliary power for the ID fans. That also reduce the capacity. That's what you can see here. It is so much of blockages are there. Here also you can see cementing has happened. That's what there is no passing of the flue gas. That's what they have to do. Once in a overall they have to clean up or they have to replace the baskets. Okay. This is one of this one. That is again for the combustion, proper combustion, your access air, it should be maintained around 17 to 20%. Okay. Why access air? Because to convert total carbon into carbon dioxide is our main aim. Because if you give only theoretical air, there may not be able to convert full carbon into carbon dioxide. What happens if you don't provide that proper this one? Okay, then your unburned, that is CO formation will be more, and CO at your boiler outlet will increase. If the CO is more, it is a hazardous. Okay, hazardous for the human being as per the that is CPCB norms. CPCB norms, it should be less than 100 ppm, and at the same time your this one ash particle, that is the particulate matter at the exit of the chimney, it should be around 150, but now again they have revised it to 100 microgram per meter cube. Okay, but at the atmosphere, at any point, this one, if you measure the particulate matter 10, the value should be less than 100 this one microgram per meter cube. Okay, but you can see here in this case the access air is more. Actually, generally it will be 3.5 to 4, but it is this one. But after APH, you can see the oxygen content is more here. Normally, delta across the APH, what we see is hardly it should be 1% increase should be there. That it depends on the leakage in the air preheater. Because what happens, your flue gas pressure will be in negative side, your air pressure will be on positive side. There will be a tendency, if there is a C leakage, tendency of air going into the flue gas is more, especially primary air pressure. Primary air pressure will be around 1000 or 1200 mm of water column, whereas secondary air will be around 200 mm of water column. But whereas your flue gas pressure at the APH, it will be around 100 or 120 minus. Okay, that's what there is a tendency. That's what in this case, in this power plant, you can see here the oxygen, leakage in the air preheater is more. That's what it is 9.1 and 8.5. Why I am showing this? This cause again additional loading on the ID fans. They will restrict the ID fans. That's what you can see here. Air preheater leakage is allowed is 13.8%. But whereas the actual measured value, you can see 38.5 and 30.7. Not only the power of ID fans, your air fans power also will be more for this. Yeah, this is again pressure drop across the ESP, even pressure drop across the ESP is more. That also causes the loading on the ID fan. Okay. Yeah, this is one of the power plant what we have seen. You see the dust concentration at ESP is actually around 1060 to 9319 microgram per meter cube is measured. Actually, as per the value, as per the design value, it should be around 100 microgram per nm cube. But during the test also you can see here 1600. What happened? This is mainly because the non-operation of the ESPs. You see, ESPs are designed for 60 kV, okay, DC voltage, and it was varying between 17 to 40 because of some problems, and current also it was varying between 40 to 200. Means it is not able to load. That collection of the plates is very poor. That's what your dust concentration at the ID inlet is very high. Because of this high dust concentration at the ID fan, every 6 months they have to change the ID fan impeller. Otherwise, ID will not create the sufficient negative pressure, because the main aim of the ID fan is to create the negative pressure of the in the furnace. If it is not able to create that negative pressure, generally in the power plant, if the pressure goes to around 10 mm of water column, it will give a alarm, and if it goes to 15 mm of water column, it will shut down the power, this one furnace. Okay, that is the condition. Okay, to maintain that, sufficient suction has to be created by your ID. But because of this high ash content in the flue gas, the impeller is getting eroded, and then is not able to maintain that required pressure, negative pressure. That's what we have suggested, to replace the ESPs with a higher. As the voltage of this ESP increases, your collection efficiency comes down. It improves. Okay. And this is another this one, and one more one of the power plant what we have seen in MSEV, that is Perli, or maybe some this one. Okay, there we have seen that they were using this ammonia injection into the flue gas. That is, by injecting the ammonia in the flue gas, your dust, that is the ash, resistivity of that will come down. If the resistivity is less, your collection efficiency of your ESP increases. You can see here chimney, that is 610 to 750 microgram, is reduced to around 130 to 190. Okay, this is, okay, you can just see. These are some of the things already I have discussed. Okay, boiler efficiency. Yeah, this. Yeah, some of the ID fan performance what we have measured, 56.18%. In that, what are all the components in that? Okay, yeah, that's what I was telling. Pressure. You see minus 5. Okay, then it goes to the this one here at economizer inlet. APH I was telling around 80 to 90. Then again ESP. These are the operating points, and this is the design value. And this is the gap between the design and operating. Okay, operating will be on the higher side, mainly because of the erosion rate, and then ingress in the furnace. Okay, and then again this is the power consumption. Okay, this is FD fan, that is the secondary air fans. Okay, in that again the pressure, this one deviation. Okay, this is the power, auxiliary power. Yeah, these are the PA fans. PA fans generally design pressure will be around 120, 1250, but operating will be on the higher side, mainly because of the leakages and other things. Okay. Yeah, this is the again power consumption. You can see this is the gap between the design value to the. These all add on to your environmental issues. That's what. And again, condenser vacuum. I was telling about the condenser vacuum. That is because of these are the condenser tubes. You can see a lot of tubes are blocked. Because of that blocking of the tubes, you can see here so many tubes are blocked. Okay, that caused your condenser vacuum less. If the condenser vacuum is less, your steam extraction will come down, and your plant efficiency comes down. And then again, cooling tower. Again, we have carried out some study in NTPC power plant, that is by replacing the FRP plan, GRP plan they were using, by replacing with the FRP plan. This one, you can save the auxiliary power. Okay. Yeah. With this, I come to conclusion, that is operating the plant at higher PLF will reduce CO2 emission, use of coal blending, reduce the emission. Okay, operating the plant near to MCR condition, that is the maximum continuous rating, your auxiliary power will come down, and your environmental issues comes down. Okay, operating the optimum access air. Access air generally we maintain around 20%. If it is more than that, if the higher access air, your dry flue gas losses will be more, and your auxiliary power by fans, draft fans, that is ID, FD, PA, it will increase. Okay, and furnace ingress. Okay, that is the major concern in many of the power plants. Okay, furnace illegal ingress cause the higher auxiliary power of the ID fans and capacity comes down. Okay, again maintenance. Okay, with all this we can reduce the auxiliary power and then performance of the plant we can improve, thereby we can control the environmental issues. Okay, with this I will come to the end of this session. I think without break I have continued, I think. Okay, if you have any questions or anything you can ask me. Okay, yeah, or you can contact me through these mail IDs. Okay, or even phone. Okay, regarding the power plant. That is what we are looking for, especially on the air quality and all. We are looking on these. This one. We have any questions or anything, you can dust concentration and SO2 and CO2. And one more advantage of Indian coal is sulfur content is less. That's what we don't have much problem with this regarding the power plants problem. That is what we are. Whereas for the imported, especially acid quality, sulfur we are looking for these, and then this oxygen is there. For that we can go for rest concentration. That is SO2 and CO2. And one more advantage you can contact Indian coal is diesel price content is less. We don't go for it. For that diesel price is even auxiliary power. That is what we are. Whereas for the import, that's what is the HANO they have installed at the system. And then this and even in Tata they had installed for 500 rest concentration. Okay. And also a lot of work is going on with cancer like carbon plants. That is what the trending for that, but the costs are very auxiliary power. Whereas for this, that's what increase the HANO they have, but still people are using. And this one is Saturday, they had started for 500 that is integrated gas. And also a lot of combined cycles. What cancer is go for first they will creating gas, but the things by using a boilers or something we generate the gas and then the gas they will take out and run the gas turbines and then cleaning whatever that is the integrated for the HRSG combined cycle. That combined cycle they are going to but it is already creating gas, but already some plants or some plants are working generating. Okay, but that gas comes then you must discuss the turbines and environmental specific may come down. This is what I wanted to share my experience with others, but it is how many questions or anything board, okay, they have brought out the norms, that is 10,000 questioning or some norm is there. They have provided depending on the capacity of the boilers, they have provided that, okay, for particular power plant. And compared to the chimney height, that is the particulate emission. Actually, earlier it was that is particulate emission, that is PM10 it was. That used to be around 150 microgram per NMQ, but now they have even reduced to 100, but it has not come in as a regulation, but it has a hand. That's what we look after in the environmental impact assessment also. Okay? That is the major concern, because pollution board also they come and check that. Okay? Not the any item per NMQ, but now they have even reduced to 100, but it has not come in as a regulation.
One question from K. Rajashekar, IEEE student, sir. What will be the scenario in thermal power plants when EVs will be used and demand increases? Is it EVs? Is it true that contrary to believe EVs will increase pollution rather than decrease it as more coal-based generation will take place?
Yeah, it is a complex question. What we can say, generally, we prefer rather than burning the fuel. See, that's what this internal combustion engines and all we are reducing it. Because the major concern with using this internal combustion engine is we have to depend on import. That is, oil is being imported. Okay, for that we are paying a lot of import. That is one thing. Other environmental issues. Okay, our main aim is go for electric vehicles. Okay, that's what we are going for, electric vehicles, and even transportation also, like trains and all. We are going for electric transport. Because compared to using this oil-based combustion, that is other environmental better choice. Okay, this our generation by using a coal economy also. We see economy in the sense the generation cost for coal-based power plant, it will vary from 3 rupees to 4 rupees now. Earlier it was even less than 2 rupees. But if you go for an oil-based installation, almost around 20 4 to 25 days per unit. You can just see economy-wise also. That's what if you go for this centralized generation, then even considering your transmission loss and distribution loss of 50%, this will give you the better economy compared to your fuel prices, whatever oil we are running. And again, oil combustion, internal combustion engines, they produce the CO. Okay, CO is a major hurdle. It is a hazardous this one. That's what we have to test all our vehicles for the combustion. Okay, but whereas in power station, the conversion from carbon to coal, CO2 will be more. CO is very less compared to your internal combustion engine. And also sulfur, that is the SOx, SO2 generation is more in the hazardous internal combustion. That's what we have to test in compared to your coal-based power plant. Okay, that's what as per the environmental this one is concerned. These EVs are better than your internal combustion engine. Even though you go for and also based on nowadays India we are going for solar PV generation in power plant. That's what our honorable Prime Minister, okay, he has mentioned that in one of the this is recent. In another 2 years we are going to go for 175 gigawatt solar PV power plant, and near Kashmir border around 30,000 megawatt solar PV power plant they have sanctioned now. Almost around 30 gigawatt at a single point, around 800 kilometers okay, area they are going to set up solar PV power plant. Okay, that way we are going for solar PV power plant. During night time we have other this one we are going for. That's what I have shown in my this one, some of the planning report, in that by 2026-27, our solar generation capacity crosses the question is concerned, even in that way, if you go for a coal-based power plant, also if you go with the EV, that is less costly and less environmental pollution compared to the internal combustion engines what we are using for the transportation sector. Is it clear? As per
Yes.
Yes.
yeah. Also, any other questions?
Up to now, I asked the questions from the chat box, sir. I request any of the participants you want to ask any question you can raise now.
Is it clear?
Yes.
Yes.
Yeah. Also, any other questions?
Up to now, I asked the questions from the chat box, sir. I request any of the participants you want to ask any question you can raise now. I think if no questions means we go for the conclusion. No questions from any participants.
Yeah, thank you all for patient listening. Okay.
Thank you, sir. Thank you for your wonderful sessions, which helps all the participants to gain the real-time practical things, which is very useful. They won't get from the textbook. So it's a very good webinar talk. Okay. Before conclusion, all the participants, we have posted the feedback in the chat box. Okay, fill the feedback. It is compulsory for the e-certificate. There will be feedback will not be posted in the WhatsApp group or anything else. So it is posted in the chat box. Before conclusion, we'll play the video of REVA University. Okay. Before conclusion, all the participants, we have posted the feedback in the chat box. Okay, fill the feedback. It is compulsory for the e-certificate. There will be feedback will not be posted in the WhatsApp group or anything else. So it is posted in the chat box. Before conclusion, we'll play the video of REVA University. Before conclusion, all the participants, we have posted the feedback in the chat box. Okay, fill the feedback. It is compulsory for the e-certificate. There will be feedback will not be posted in the WhatsApp group or anything else. So it is posted in the chat box. Before conclusion, we'll play the video of REVA University. Before conclusion, all the participants, we have posted the feedback in the chat box. Okay, fill the feedback. It is compulsory for the e-certificate. There will be feedback will not be posted in the WhatsApp group or anything else. So it is posted in the chat box. Before conclusion, we'll play the video of REVA University.
Sagar, that audio is not coming.
Thank you all for your patience. Okay. Thank you.
Thank you, Priya and all others. Okay, thank you.
Thank you, sir.